So this is a very interesting course on basic control systems that we are starting this semester, and today we are going to see the syllabus for the course, the books recommended, and briefly try to understand what consists of the 5 units, right? And unit first is about control systems. Basically, it's a 4-credit course, so you have basically 3 lectures, 1 tutorial, and there is a separate lab course for this, so that is not included in this. So in the first unit we'll be talking mostly about control systems, their examples, classification. We'll be talking about the open loop and closed loop control systems, their differences. We'll take up transfer functions, modeling, block diagram representation, signal flow graphs, and then reduction using Mason-Gaines formula, and then we'll talk about models of some industrial control devices and systems. So the first unit is mostly about introduction. It is mostly about introduction, and it is about some modeling, right? There are 2 types of models that we are studying here, 2 types of mathematical models that we're studying here. One is the transfer function model, and one is the state variable representation. And then there's also some model simplification that we're going to study in this. So block diagram representation and signal flow graphs are ways to simplify the model that we're studying. Okay. In the second unit, we're talking about test signals, time domain performance of first and second order control systems, so on and so forth. And then we talk about standard proportional integral derivative control system characteristics. The third unit is about stability. Stability is a very important feature of a very important thing that we study in control systems. It's very basic to control system design. We talk about stability, the concept of stability, and how is stability related to the roots of the characteristic equation, and then we talk about some methods to actually check stability of systems. The fourth unit is about a design tool, a design and analysis tool called the root locus analysis, and also about another analysis and design method, which is in the Bode diagrams, the Nyquist plots, frequency response analysis. These are basically tools to actually understand and design controllers and see system performance. The last unit is particularly about design of controllers. So in the first 4 units we basically lay the basis for understanding control systems and analyzing control systems, and in the last unit we actually design a controller for a system that we want to design it with. So coming to the first unit, right, and starting with the first unit. So today we are going to understand what is the motivation. I hope that this whiteboard is clear. You're able to see what I'm writing. What is the motivation for studying control systems, right? What is the motivation for studying control systems? So the basic motivation is that actually, if you see, the engineer is supposed, if you see, the engineer is basically supposed to control things, to design and control. That's what his basic objective is. So so these things, these objects, they may be natural, right, or they may be man-made, right? So the basic the basic job of an engineer is actually to design controllers so that systems, so that things have a particular response that he wants those systems to have, right? And control systems are very prevalent. Control systems are very prevalent in nature, both in the natural world, right? Both in the natural world and in the in the man-made objects that you see around you, right? So how do you basically define a control system? A control system consists of processes or plants assembled for controlling outputs, right? So the basic definition is actually, if you look at the definition for if you look at the definition for control system, broadly you can say that you have a collection, you have you have some subsystems or processes, you have subsystems which are parts of a system, right? You have subsystems or processes because we also control processes in process control systems, like the process of manufacturing something, or plants, right? Plant is these are all used interchangeably in control systems. So you have subsystems, processes, or plants that you're trying to whose outputs you're trying to control, whose outputs are being controlled. And they are being controlled because you want to achieve a desired objective. You have a desired objective, you have a desired output, and you want to achieve that objective or that output. So this is a control. This is the definition of control system, right? And what is so important about it is that you have them everywhere, right? Even the human body that you see, any process that you see inside the human body, it's actually most of the processes are closed loop control processes. Like for example, when you exercise, you sweat, and that sweat is because you after you have exercised, right? You have exercised or you have done something strenuous. This leads to a process of sweating, right? And this sweating is because your body has actually heated up, you're hot, and your body wants to reduce the temperature. That temperature is reduced because there is a mechanism inside that allows you to sweat. And once this sweat comes out, an evaporation that takes place because consequently causes the body temperature to be reduced. So here you have a desired objective. Actually, in the natural world, the objective is to keep the body temperature at a particular level. So you want to basically regulate the body temperature, and so there is a sensing mechanism inside, right? There is a sensing mechanism which tells the body that the temperature is not right, or it is risen. And then there is something that operates inside which causes this sweat to form, and for it to be released on the skin, and which actually leads to regulation of the body temperature because of evaporation, right? In a similar way, to give another example from what we see every day in our daily lives, is for example, how do you cross a road, right? You're about to cross a road, right? So there's a road and there's a vehicle coming from one side, and you're here, somewhere here, right? And you want to cross this road. So you look at the vehicle, you judge, and this judging is it's not calculative, it's very intuitive, but you're able to judge the distance, not exactly, but at least approximately. You're even able to judge the speed, so you're able to judge the distance, you're able to judge the speed, and then you decide whether you want to cross the road or not, right? So if you feel that your distance and the speed are such that you can cross the road, you cross the road. If you feel that the distance and speed are such that you'll not be able to make it to the other side, you'll not cross the road. What happens if, for example, suddenly when you're about to cross the road, the driver increases the speed, right? So you have your eyes on the car and you're looking at the car, and suddenly the driver is increasing the speed. Once he increases the speed, the moment you see him increasing the speed, you'll come back, right? You'll come back. You'll change your decision. You'll understand now that you cannot cross the road, or you're in danger if you cross the road. So basically, this is a classic example of control system where actually you have taken a decision on whether you want to cross the road or not, depending upon this distance and speed. So you have a sensing mechanism here, right? The sensing mechanism is your eyes, right? Are your eyes, even your ears, because you're able to sense the distance to some extent using the voice, using the noise that is coming to your side. And then also uh, the decision to come back and not cross the road is because there is a feedback loop. You're continuously checking the speed of the car if you're looking at the car, and then you suddenly decide, no, it's not the right thing to go and cross the road, so you come back. So 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 your body movement is controlled because the inputs have changed, and this is how we're actually applying control systems without actually knowing that you're applying control systems, right? uh, there can be many other examples from the natural world. The way your sugar is regulated in blood, right? Sugar regulation takes place through an organ called the pancreas, right? And this is also an example of control systems being applied. And you have these days in fact control system ideas and technologies employed to tackle this problem of sugar level regulation in the blood for diabetic patients, and the process that they employ is basically rooted in control systems, right? I could give you many other examples, but there we have a time limit in Zoom meetings, so I will not waste any more time in this. This is just to tell you that it is something very prevalent around you in the natural world, and in the man-made world, of course. Yes, in the man-made world also you see controllers almost everywhere, right? So I'll show you some slides from the book. I forgot to mention the book. Right, just a second. I'll once again go back to the syllabus. Right. So the basic book that I'll recommend is this control. Okay. So the fundamental book that I'll recommend, this is going to be your textbook, Control Systems Engineering by Norman S. Nice. I'll also be showing you some slides from this book during the course of this lecture. And then there are some other very good books. This book by Madan Gopal, Control Systems Principles and Design, is also a very good book. And then there are two other books, right? So the syllabus and the book recommendations are already in the classroom, right? I've already shared it with you. So I will be primarily teaching from Nice, but maybe some examples, some questions from other books also, right? Okay, so now let us see some slides from the book, right? Okay, so this is how control system is defined. Actually, you have an input or a stimulus, and please note that input or the stimulus is also the desired response, right? This is very important because when I talked about the human body and temperature regulation within the human body, I told you that the temperature has to remain within some limits, right? So the temperature has to remain within limits and has to remain within limits. So if your temperature is beyond a particular point, then your body should react to it, right? So this is actually a desired temperature that you feel, that is fed to the human body, right? So the desired temperature is that the temperature has to remain within a range, and this is actually this input to the body, right, which is kind of built in the body. And then you have a control system actually, and then your body has a certain output or a response, which is the actual response. And basically you would like to your desired response and your actual response to be similar, right? And that is what is the whole design process about. So this is an example of elevators, which are classical examples of control systems. Like you like an elevator to start and take you to a particular floor, and it cannot move too fast, it cannot move too slow, and then it has to reach that particular floor in a with some amount of accuracy, right? So this is also, these are slides from your book which has been recommended. So this is a picture of these are man-made control systems around you. This is a rover that was built, a robot that was built around 1979 to remotely check contamination at a place where a nuclear accident had happened, right? So again, an example, a very relevant example of control systems being applied in everyday life, right? This is a slightly old technology now. How does a CD, a compact disc, how is it read using a laser disc player? So it's actually bits on the disc which are read optically, and there is a whole control system feedback loop around it, so that this reading happens correctly. The audio and the video is read correctly. Okay. Now let us look at this example of elevator input and output from this, so, and try to understand what is this uh, desired response and actual response. So suppose you want to go to floor number 4. So you have this is your on the x-axis you have time, right? And on the y-axis you have floor, right? Please see this, this is very important. So your input is floor number, you enter the elevator and you ask the elevator to take you to floor number 4. So this is your input command. You suddenly go in and say, take me to floor number 4. So this is your input. So your input remains constant throughout. You want to go to floor number 4. Now your output cannot be, now this input is also, please remember, this is also the desired output, right? Your desired, what is your desired output? You want to be taken to floor number 4. Where are you right now? You're at floor number 0, right? So this is the desired output, and now your elevator is going to respond to this input. It is going to take you to floor number 4. There is a whole control system design inside the elevator. There are motors, there are many other things, and there might be a small microcontroller inside, right? And there might be alarms and other things to actually take you to floor number to